Hi friends, very good evening, and let me just adjust my screen view quickly. I hope everybody can see my screen now. Let me also put it up. So could you please confirm on Slack if you're able to see my screen and if you can hear my voice? Can you please confirm? I don't think you'll see the black screen now. I've just changed the settings. Yeah, you should be able to see my screen. Could you please confirm if everything is all right? Yeah, I just opened the Slack window. Okay, good. So there are no glitches. That's good to know. Good evening, folks. Thank you for joining in. We'll start the session in a couple of minutes. I've already shared the notes for today's session. I've already posted it right here. So you can just go here and you can keep the notes open if that helps you. All right. So, I just posted it early today just to see how that works out. Okay, cool. So things are looking good. Good. Okay. We will just start in a couple of minutes so that everybody can join in by 7 p.m. India time. Okay, so we'll just get started in a couple of minutes. So I have some notes that I've prepared, which I've shared with you as a PDF. We'll probably require about 3 sessions to complete to get a good overview of Spark. We'll see how it goes. I don't want to rush through it. I want to give as much in-depth knowledge which is relevant in the context of AI and machine learning as we can. Cool. One more minute and we'll get started. Okay. Hey, good evening, folks. Okay. Okay. Somebody seems to have a problem. Please quit the app and restart it. So, okay. Okay, so I've enrolled in this course and currently enjoying the content. Happy to hear that. I wanted to ask whether you guys are able to help get into research-based roles with companies that publish in top conferences like CVPR, NeurIPS, ICML, etc. Again, please understand that we are not at all research focused, so we will not be looking into research publications itself. So we will not be able to help you get a publication in CVPR, NeurIPS, ICML, etc. But some of our students who have gone on to companies like Amazon, Flipkart, etc., they do publish in these conferences, right? So they all apply machine learning techniques. They all apply machine learning techniques to solve real world problems, but they also publish in conferences like this, right? So while we don't help students publish in CVPR, ICML, etc., because that's a different cycle altogether. We are more focused on helping you transition to a machine learning job. Again, some of our students have gone on to work in teams. Like, for example, in the previous team that I was working on at Amazon, it was not mandatory for us to publish in ICML, CVPR, etc. But if we wanted to, we could. There was a legal process that we had to go through internally, and then we can publish. So there are such teams also. Okay, somebody has a problem, so please call us on the phone number listed on the website. Okay, so somebody will help you there. Cool. Okay, let's get started right away. And again, this will be recorded and it will be provided on our website, on our course web page also for later viewing. Okay. So the objective of this whole session, or the sequence of sessions, I don't think we can finish all of Spark in one session. So this is going to be a sequence of sessions, is learning Spark primarily from a data science or a machine learning or AI perspective. Please don't expect this to be a thorough, in-depth explanation of Spark, because understanding the whole Spark platform, the internals, the nitty-gritty details of Spark is typically a 100-hour course onto itself, right? Which is something that you can cover in a big data course, right? So we are not going to go into the nitty-gritty details of a big data developer or a Spark developer. We are not doing that. We will mostly focus on using Spark as for primarily data science, machine learning, and AI applications. Okay, it's very important to understand the context here. This is not to become a Spark engineer, but to be a user of Spark for these applications. Okay, so I'm assuming we would need about 3 sessions to finish this. Okay, let's get some historical context because that will help us understand where we are today and how did we reach here. Okay, so if you look at the whole distributed machine learning, the whole space of distributed machine learning, or in general distributed scientific computing, because if you think of machine learning, what you're running is basically a bunch of mathematical algorithms and a lot of scientific computing, whether it is nuclear research, whether it is weather forecasting. There are a lot of problems in physics, chemistry and biology, whether it's understanding genes, all of that are all part of scientific computing, right? So machine learning is one type of scientific computing task which uses mostly optimization algorithms. Okay, so the way things panned out was pre-2006, when I was an undergraduate student, the most popular distributed scientific computing platforms were MPI and PVM, right? MPI being the more popular one. MPI stands for Message Passing Interface. Now, what is this whole thing about distributed computing? The essence of distributed computing is this. Imagine if you have multiple computers, right? A computer has a compute element, typically like a processor. It has memory and it has disk. Disk basically means your solid state drive or hard disk. These are the three, broadly speaking, these are the three components that we care about from a computational standpoint. So imagine if you have multiple computers, right, with compute units, typically processors, memory, which is typically RAM, and disk, right? You can have multiple computers like this. All these computers could be connected via LAN, like via Ethernet. You might have seen Ethernet cables, right? So these are typically connected on a network, typically a local network. Like typically what happens is there are multiple of these computers, all of them in an air conditioned room, and they're all connected through a LAN. Now you want to use, so distributed computing is all about taking a big task, like for example, build a machine learning model on 1 billion data points, right? That's a big task. So split that across multiple computers. This is one type of distributed computing. Okay, there is parallel computing, there is multi-core computing. It's a big area. We will only focus on distributed computing, whose primary purpose is, given a big task like training a machine learning model on large data set with billions of points, how do you distribute it across multiple computers like this, which are connected via LAN? Each computer has a compute unit, memory, and a disk. Okay, just a small detour here. The way we'll proceed is, I'll cover these concepts for about, let's say 60 to 90 minutes. I don't know how much time will exactly take, but I'll cover the concepts first. Then we will spend about 30 minutes wherein I will try to answer as many questions as you folks have, right? So that we can make progress with the content, and at the end, we can discuss about a lot of questions that you have. In the previous sessions, we try to answer most of the questions. Again, many questions that students ask would get covered in this 60 to 90 minutes that we'll go through the first notes. Okay, so that's important, right? So, okay, so the whole concept of distributed computing is, how do you use multiple computers that are connected via LAN to do this? So there was this system called MPI. I've written some code in MPI when I was at Indian Institute of Science, because they have a very large distributed supercomputing center. And they use something called as message passing interface. It was extremely hard to write code in this. It is very, very cumbersome. It is very, very cumbersome, because it's like literally writing low-level Linux code. Okay, if you've ever written low-level Linux C++ code, that's how hard it is to write message passing interface code. It was very, very hard. Then around 2006, there is this platform which came up called Hadoop. Again, Hadoop is an open source project which is based on the concept of MapReduce. I'll explain you what MapReduce is in just a few minutes. MapReduce is a computational model, right? MapReduce is a very simple distributed computational model. I'll explain you what I mean by distributed computational model in just a few minutes. Bear with me. So the whole Hadoop thing came up because in the early 2000s, in the early 2000s, Google, which was one of the most technologically advanced companies even today, they started noticing that they're crawling this whole internet. They have huge amounts of data and they want to process this whole data. So engineers at Google came up, again, MapReduce as a concept has existed for a very long time in distributed computing. MapReduce as a concept is not something that Google invented. It's been there for a while. In early 2000s, Google started using this whole concept of MapReduce, and they were sitting literally on, they were literally crawling the internet, right? So they were sitting on large amounts of data and they want to run a bunch of algorithms on it. Okay, bunch of algorithms. So they decided that if they buy supercomputers, they'll become just simply very, very expensive. So they came up with a very nice idea. Okay, this is by the team that was led by Jeff Dean, a phenomenal engineer, a distributed computing PhD, and I think he's a VP or senior VP of engineering now. Phenomenal guy. And his team came up with this whole idea that what if I use simple computers that are available in the market? Simple motherboards, actually, not even full computers. Let's take motherboards. The motherboard has a compute unit. It has RAM or memory. I can also connect a disk to it. So they took motherboards like this. They connected multiple motherboards with compute, memory, and a disk. They connected all of them to LAN. Okay, these are all like, you could go to a shop and buy a motherboard, put a microprocessor on it, like an Intel processor, add some RAM to it, add some hard disk to it, and they connected all of them through LAN. So they took off-the-shelf, readily available motherboards with compute unit, memory, and disk. They connected it via LAN, and they said, why can't we use this concept of MapReduce, which has been studied in distributed computing for almost a decade? Why don't we build a system of our own on top of Linux to be able to process all of this humongous amount of data that we are anyway having, right? So phenomenal idea, right? And I think around 2003 they published this research paper. 2003 or 2004 they published this research paper called MapReduce. Very interesting paper. Then a bunch of open source guys said, okay, let's build an open source MapReduce platform called Hadoop. This is something which got launched in 2006. I joined Yahoo Research, or Yahoo Labs as it was called then. I joined Yahoo Labs in 2009. This was the time when Hadoop became very, very popular. And I was very lucky because right after graduation, I started working on Hadoop for machine learning and data science applications. So I was in those teams which are some of the early adopters of Hadoop for machine learning and data science tasks. Around 2014, so the 2006 to 2014 is fully Hadoop era. Hadoop has its own problems. I'll explain you what those problems are in a while. But I want to give you a historical perspective. But Hadoop was much, much more easier to use than MPI. Like we could teach people how to use Hadoop in a week. MPI was much, much more cumbersome, right? Then around 2004, this was the time when I was at Amazon. So in 2014, there was this new system that started becoming very, very popular called Spark. Spark improved upon the fundamentals that Hadoop built, and it became one of the best platforms for state-of-the-art distributed machine learning and data science. So today, Spark is the most popular choice if you want to do distributed machine learning as of today. And again, I was very fortunate that I got the opportunity to build, to be one of the early adopting teams at Amazon to use Spark for machine learning and data science applications. So I saw this revolution happening in front of my own eyes. I did a little bit of MPI, but not much. So I have some first-hand experience on how my teams at various companies have used both Hadoop and Spark for machine learning applications. And I'll try to build upon those experiences here. Okay, cool. So just a quick summary of things, right? Again, we'll come to the computational model, all of that. So Spark today is the most popular system for data science, machine learning, and AI applications for large data, right? So around 2013 to 2014, when Spark actually was launched, it became a very good alternative to Hadoop. Again, my team, we were doing a lot of Hadoop stuff, but we slowly moved everything to Spark around the 2015-2016 timelines. Now, one of the biggest advantages of Spark over Hadoop was it was simply faster. Very simple concept. It was just simply faster. And it was more suitable for iterative tasks. I'll explain what I mean by iterative tasks. Okay. So for example, imagine if you have a for loop in your code. What is a for loop? For loop basically means whatever you have here, you will keep iterating through this. You'll keep running whatever is there in this loop multiple times. That's what is called an iterative task. If you see most machine learning algorithms, most machine learning training algorithms, if you have studied machine learning, again, I understand that some of the students could be in the early sections of the course videos, so you may not understand everything that I'm talking about, but don't worry, as you progress through the course, these will make sense. Most machine learning algorithms, most machine learning training algorithms involve running something in an iterative system, right? So Spark was much more suitable for iterative systems than Hadoop was, because I know this firsthand because I actually built machine learning models with my team both on Hadoop and Spark from scratch. And Spark itself was built at a very interesting lab called AMP Lab out of University of California, Berkeley, which is one of the, I mean, UC Berkeley or University of California, Berkeley is literally a legendary university in terms of both distributed systems, operating systems research, even machine learning research. Right, so it was built. It came out of a research lab in Silicon Valley. Berkeley is not in Silicon Valley, but very close to that. And it was taken up very quickly. And the team that built Spark, they started a company called Databricks, which does pretty good, which helps companies use Spark. Okay, cool. So first, before we go into Spark, let's understand Hadoop first. Okay, so that because a lot of things, whatever is there in Hadoop, you can use the same concepts in Spark also. So Hadoop has many things. The two most important things in Hadoop, again, let me just go to the comment section and see if there is any problem. Okay, so people are asking questions. Please increase the volume. I thought the volume was okay. Let me see. Sound preferences. Yeah, it'll just blast in your ears if I just increase it anymore. I don't want to just blast sound. Okay, let me increase it slightly. But I think just putting too much sound will hurt you. Again, you can increase the volume on your, I don't want to put it at 100% because it will pick up a lot of noise. Okay, cool. So I'll answer some of these questions in the sessions. For now, let's first cover all the concepts. Okay, cool. First, let's cover the concepts. I'll also do code walkthroughs, all of that as part of this series. Okay, I'll do some little code walkthroughs today, but we'll actually do it over the next few sessions. Most likely we'll finish whole of Spark in 3 sessions. Okay, cool. So first let's learn the basics of Hadoop. Understand the computational model, right? Hadoop itself has 2 fundamental chunks. There are many other things in Hadoop. Again, as I told you, we are not doing the big data course. We are learning Hadoop from data science applications and machine learning applications. There is a computational model called as MapReduce, and there is a data storage system called Hadoop distributed file system, right? So let me try to give you a simplified understanding of this. I'm giving you a high level overview so that which is sufficient to understand the basics, right? If you think of a simplified model of a distributed computing system, what you have here is you have one box here. I'll call it a box, right? This is box 1, box 2, box 3, so on and so forth, box n. We have n boxes. All these boxes are connected via a network, a very high speed network, typically 1 Gbps or even 10 Gbps networks. You have compute, which is typically 1 or more processors. You have memory and a disk, right? So there are 3 big pieces. Okay, all these are compute. Again, this is most simplified model of what a distributed system is. Now let's see how HDFS and MapReduce fit into this equation. Okay, so sorry. So to understand this, let's take a simple example. This is the hello world of MapReduce. Okay. So imagine we have a task. Let's take a very simple task and understand MapReduce from the perspective of this task. Okay. Also understand HDFS from this task. Suppose we have a big file. Okay. Suppose we have a large distributed file. Let's assume this is 1 TB file. Let's just assume, or let's for simplicity, let's assume this is a let's assume this is a 300 GB file. Okay, let me put it that way. I'll tell you why I'm taking 300 GB, right? This 300 GB file is not stored in one disk. So HDFS is Hadoop distributed file system. It's a distributed file system where this whole 300 GB of data is going to be stored in multiple part files. There are 3 parts to this whole file. So you have part 1, part 2, part 3. These 3 files are stored on 3 different disks. So part 1 could be stored in this disk. Part 1 could be 100 GB. Part 2 is again another 100 GB that is stored here. Part 3 is another 100 GB. Okay, that's what I mean when I say distributed file system, right? So, I mean, this is something that is built on top of the regular Linux file system that you have, right? So now imagine you have a distributed file which is 300 GB where you have some text. Okay, you just have some text. Let's assume this text is all the articles on Wikipedia. Let's just say this is all the articles on Wikipedia. Now what I want to do is I want to take this whole data and I want to count the frequency of each word. For example, I want to say word 1 occurs in whole of Wikipedia 12,568 times. Now word 2 occurs 116,124. I'm just writing some random numbers. So we want to generate this output. What we have is just all Wikipedia articles. Okay, let's assume just for simplicity that all of the data is 300 GB. We have broken up into 300 GBs. Okay, part 1, part 2, part 3. We are storing it. Let's assume we have 3 boxes just for simplicity. What we want to generate here is we want to generate frequencies. We want to count how many times word 1 occurs. So word 1, number of times it occurs in whole of Wikipedia, in this whole 300 GB. Let's assume that's what we want to compute. Again, this is one of the simplest examples to understand MapReduce. Again, understanding MapReduce is very important to understanding the computational model of Spark also, because Spark also uses MapReduce to some extent with some changes. Okay, now comes a very interesting question. Okay, remember in any distributed system, you want to have fault tolerance. Okay, this is a concept that if you're a computer science student, you may have learned this in databases or operating systems. If you're not a computer science student, let me explain what this means in simple terms. Fault tolerance basically means, imagine if this computer goes down for some reason. For some reason, this computer goes down. Your whole system should still be able to work. That's what fault tolerance means. It means in case there is a fault in one of the computers, the whole distributed system should be tolerant to that. So to again imagine my whole 300 GB file is stored as part 1, part 2, part 3, right? So you have part 1 here, part 2 here, part 3 here. Now imagine this whole computer goes down for some reason. The hard disk got corrupted or the network went down. For some reason, or there is an electrical circuitry problem. This whole thing went down. Then you have lost the whole P3, right? You have completely lost P3. You have completely lost these 100 GB of data. So to avoid these problems or to facilitate fault tolerant system, what HDFS does is it duplicates data. It's a standard solution in distributed systems. What it does here is P1 is stored here, but P1 is also stored in another disk, like a backup copy. P3 is stored here, a backup copy is also stored here. P2 is stored here, so you can store P2 also here. Now imagine if this box goes down. I know that P3's backup is there on this computer. This is called as fault tolerance by duplication. By duplication, it's also called as replication. It is fault tolerance by replication or duplication. When I say replicate, I mean duplicate basically means keep one more copy. I can replicate it as many times. Okay, instead of keeping one backup copy, I can keep 2 backup copies across multiple computers. So what HDFS does, again, there is a lot of internals about the design of HDFS, the operating system internals, the networking internals. I'm not going into it. So HDFS is a fault tolerant distributed file system that both Hadoop and Spark use. Okay, so we know the task right now. We understood the basics of HDFS. Very basic intuition behind it. Okay, cool. Now the whole MapReduce itself has basically 3 parts. There is a map, there is a shuffle stage. There are 3 stages. There is a map stage, there is a shuffle stage, and there is a reduce stage. Any code that you want to write on Hadoop, you have to break up the code into 3 chunks. What is your mapper? How do things get shuffled? And how do you reduce? Look at this. This is called the computational model. The reason it's called the computational model is whenever you're writing code on your computer, look at this, whenever you're writing code on your computer, what all constructs do you have? You have for loops. You have basically loops, right? You have if-else conditions. Like these are all constructs that you have, and any real world problem you want to solve, you have functions, you have classes, right? you have modules, if you're looking at Python, right? So anything that you want to implement has to be broken down into these fundamental units, right? Similarly, anything that you want to write on Hadoop has to be broken down into these 3 stages. Okay, let's solve this problem. Counting the frequency of words in a large distributed file. Let's think about it quickly. Okay, so first stage is the mapper stage, or also called as a map stage, right? So in the mapper stage, what I'll do is this. Imagine, okay, look at this. In the mapper stage, what I'll do is this. Look at this. I have my P1 here. Again, I've not drawn the backups here. Let's just look at the primary partitions or primary parts of the whole large file. This is my P1, this is my P2, this is my P3. So on this computer, on my box 1, this is my box 2, on my box 3. On my box 1, all of this is loaded into the memory. Whenever data is there in the memory, you can start computing, you can start running some code on top of it. So whatever is there in this part file is accessible to this compute unit or to this processor via the memory. Same thing, whatever is there here, you can compute something using this processor. You can compute on this using this processor. So in the mapper, look at this, there is a mapper. So whatever you write in the mapper gets executed on each of these boxes. So mapper is typically a function that you write. You write a function and say, this is my mapper function. In Hadoop, you can write this in Java, or you can write it in any programming language of your choice. Java is the native programming language of Hadoop. Whole of Hadoop is written in Java. But it's very easy to write a mapper function in any programming language, including a Linux shell script, right? So don't worry about it. You can write it in Python. I've written it in Perl. I've written it in command line also. Okay. So let's see. So a mapper basically is a function. You write a function basically. In Python, you can write a function and you can say, this is my mapper, right? Or you can write it in C also. I've written some code in C also. Okay. So our mapper, what it does is this. Again, the mapper runs independently on box 1, box 2, box 3. So the mapper, the same function runs on this data, the same function runs on this data, the same function runs on this data, but on this compute unit. Okay. Imagine if this is my file, okay, which contains word 1, word 2, word 1, word 3, word 0, sequence of words. What I will do is my mapper should try and convert this into key value pairs. Remember, in dictionary, we have key value pairs. Okay, effectively, what you should do here is, given anything like this, you want to convert into a pair with comma separated values. Okay, so this is called the key, this is called the value. So to compute the number of words, what we'll do here is, again, the same function, the same mapper function is executed here, here. When it is executed here, it's executed on this data, it's executed on this data, here it's executed on this data. So in each of these computers, what I'll do here is, imagine this is my file. What I'll do here is, I'll load this whole 100 GB of data in chunks, and I will count how many, for each word, how many times does it occur in this data. Okay, I'll just count it. And that's simple, right? How do you write this code? It's actually very, very simple to write this code. You create a dictionary, very simple. This function, all you have to do here is you have to create a dictionary, make every word that you encounter as your key. Suppose you encounter WI, make it a key. Your value is, you initialize your value to 0. You keep incrementing it. So you simply iterate through the whole text file that you have. And if you encounter W1 the first time, increment it, make the value 1. Next time you increment it, make the value 2. Keep incrementing it whenever you encounter it. Very simple. You're just counting how many times each word occurs in these files, right? So this is called the output of the mapper. Cool. So you have to always break down your code, or any logic, anything that you write on Hadoop has to be broken down into mapper, shuffle, and reduce. Okay. To solve this problem, this is how I wrote my mapper. Next, let's see what happens in the shuffle stage. Okay. I've drawn this diagram. Okay. Let's assume these are the outputs. Again, my mapper, let's assume my mapper, which ran on this box, said W0 occurs 1 time, W1 occurs 2 times, W3 occurs 4 times, W4 occurs 2 times, and so on and so forth in this part file. Right. So here This box 2 said, okay, these are the counts for each of the words. And again, here if you notice, W3 does not exist because W3 may not exist in this whole file, right? Similarly, these are the individual counts of how many times each word occurred in part 3. Now, shuffle stage is where the computer network plays the role. What shuffle does here, very interestingly, what shuffle does here is, shuffle says everything that has W0. Okay, there is W0 here, there is W0 here, there is W0 here. What shuffle does is, it swaps this data, it moves the data literally across this whole LAN network, and it says all the, look at this, what you basically have are key value pairs now. Wherever the key is the same, which means wherever you have this W0, wherever you have the same key, place all of them in the same box. Okay, so that's what shuffle does. Shuffle now takes this data, moves the, so basically what it's doing here is it's moving this from this computer to this computer. It's also moving this from this computer to this computer so that all of W0 is in one chunk. So what shuffle guarantees to you is anywhere where the key value is the same, they all will get grouped together in the same box. And after shuffle, whatever you have is stored as a temporary file. This whole result is stored as a temporary file on the disk. I'll tell you why it's stored as a temporary file in just a few minutes. Now, if you notice this, look at this. If you notice this, wherever you have W1, all of them got shuffled such that wherever the key is the same, they all got grouped. But in this case, look at this. You have both W1s and W2s. Okay, so multiple keys can go to the same box, but you can't have a system where some W0s are here, some W0s are there. No. So wherever key is the same, it all goes to the same box. And even this whole resultant is stored in a temporary file here. This whole thing is stored in a temporary disk file here. Okay, very simple logic, right? So what is happening? In MapReduce, in Mapper, I took my input, I converted into key value pairs. My shuffle ensures that wherever the key is the same, by using the computer network and some temporary storage, it shuffles the data such that wherever all the similar keyed entries, okay, all the similar keyed entries get grouped together. Look at this, all of W4 is here, all of W5 is also here, right? Now, why are we storing everything into disk here? To create fault tolerance. So imagine, let's look at worst case scenario, okay? Suppose, okay, this whole mapper got computed, this whole mapper got computed, this whole mapper got computed, okay? We also shuffled, okay? If you do not store it on disk, the biggest problem it runs is, what if before you shuffle this box goes down? So all of this result goes for a toss. So Hadoop now writes everything to a temporary disk here. So after shuffling, this whole resultant is stored onto the disk. So that even if something goes wrong, again, when it stores in the disk, it also replicates on the disk. Okay, so that if any box goes down, it can always use the backup, right? So now after it shuffles, this is where things get interesting. Now you can write a reduce function. The way reduce works is, whatever you have stored in the temporary storage here, look at this, whatever you have stored in the temporary storage here, right? Reduce function, you will also write a function called reduce, right? So in MapReduce, you have to write the map function, what the map function should do, and what the reduce function should do. Shuffling happens automatically by the Hadoop system. The Hadoop system shuffles it automatically for you. You don't have to write the shuffler, right? You just write the map function and you write the reduce function. In the reduce function, because I know that all W0s got congregated at the same place, in the reduce function, I'll simply say, whatever is this output, please go line by line. And as long as I have W0s, just sum up all of them. So what will happen now? When I run, I'll write my reduce function in Python again. I'll write it in such a way. Now, what am I doing here? I'm saying, so what will happen here? My reduce function simply goes line by line. Wherever W0 is, wherever these values are same, it will just count it up and write it to disk. It will write the output, right? So when it generates the output, it will say W05 and it will write it in the output folder. Similarly, if you look at this, Okay, it will go line by line, W1, same W1, so it will sum up both of them. When it goes here, it becomes W2. Okay, so you implement your reduce such that you read this line by line, and whenever these values are the same, you sum it up. So here the values, the keys are the same, I'm sorry. Whenever the keys are the same, you sum it up. So on this box 2, you will get W1 3 and W2 8. On this box, you will get W4 8, W5 10. Now all these results, you store it back to the disk into the output folder. Now what do you have in the output folders? Now again, remember that your output folder is also distributed. This is your output, this is your output here, this is your output here. So now if you look at all the outputs, in the outputs you are getting the number of times W0 occurs across P1, P2, P3. You are getting number of times W1 occurs across P1, P2, P3. The number of times W2 occurs across P1, P2, P3. So if you want to do a very simple task like counting the number of words, this is how you translate that code into a MapReduce system. Imagine if you were to do it in a regular computer. If you were to do it in a regular computer, how would you do? Suppose single box, W1, W2, W1, W3, W4, so on and so forth. How do you write the code? You write a for loop in a simple system, right? You keep counting and you create a dictionary and you say W1, so key is the word, value is the count. This is how you write the code if it's a single box system. If you want to write the same thing in Hadoop, you have to implement the map function or the mapper. Shuffler you don't have to implement because the default shuffling, the way Hadoop shuffles is anything which has the same key will all get shuffled and they all will come to the same box. Okay, shuffle you don't have to implement, you just have to implement reduce. So what is, if you look at it, any program that you write, you just have to write the map function, you have to write the reduce function. This has made life very, very simple. Because all of my data is in HDFS, I don't have to worry about it. All I have to do now is write a map function, write a reduce function. So any real world task that I have, if I can map it or if I can convert it into a map and a reduce function, I'm done. Right? So coming from MPI world, Hadoop was literally magical because I came from the MPI world and I started using Hadoop and it felt like, wow, I could write Hadoop scripts in like 10 minutes with some practice. It requires some practice to writing it, but you don't have to write it today because things have improved enormously. Fortunately, I got the opportunity to be in the front row when whole Hadoop and Spark were being developed at various companies. Okay, cool. What are the biggest advantages of Hadoop? The biggest advantages of Hadoop is it can easily scale to thousands of nodes or thousands of boxes. When I say nodes, I mean boxes. The distributed computing terminology is nodes, right? So again, my team used 2000 node Hadoop clusters and all I need are commodity boxes that I can go and buy. They're very cheap. They're not some specialized hardware. They are not some supercomputers from Cray computers where I have to order, I'll have to wait for 2 years to get it. We could spawn a 2000 node cluster in minutes, literally in minutes, or maybe worst case a couple of hours. Right? We were doing this in practice. And the best part here is the programming model is extremely simple and you get HDFS along with it. The communication model, which means how do computers talk to each other? Right? How does data get shuffled? Again, look at this, the communication model, or in other words, how does data move from one computer to other computer is based on shuffle. It's a very simple model, right? Because MPI has a very, very complex message passing system. Very complex system, to be honest with you. It was a nightmare writing code. And the whole MapReduce framework is very good for database operations. If you want to join tables, if you want to group tables, right? So these are the typical operations that you have seen in SQL, right? You want to join tables, you want to group, or you want to co-group, you want to sort, you want to perform some simple numerical operations. MapReduce is very, very good for database operations. So a lot of people started using Hadoop for storing large data. Now, while that was happening, around 2000, I forgot the exact years. I think around 2009-ish or 8-ish, at Yahoo Labs, there was this whole language called Pig, which was created. So Pig was literally, imagine if your data was on HDFS, Pig gave an SQL-like language in which you can write scripts. Again, remember that writing code in MapReduce for all the tasks is still cumbersome because you have to, suppose you want to join two tables. Let's ask that question. Suppose you want to join two tables, right? Suppose you have two tables that you want to join. Now translating that into MapReduce every time is cumbersome, right? You have to think very deeply. So what researchers did to make it simpler for people to use, especially software engineers, is distributed systems research teams at Yahoo built a language called Pig, wherein you can write code in an SQL-like language. You can say join A and B, right? You can write SQL-like language. So you don't, again, what it would do is if you write in Pig, it's called the Pig Latin. It's very SQL-like language, not exactly SQL, but SQL-like language. It would take whatever you have written, it would convert that into a sequence of MapReduce jobs. It would convert that into a sequence of MapReduce and it would execute the whole thing, right? So this was built at Yahoo, and again, I got to see how it was designed. I mean, I was very lucky, to be honest with you. So I used Pig extensively at Yahoo, Amazon, etc. Then Facebook came up with a very interesting tool. Facebook was also becoming a big company at that point. Facebook built a tool called Hive. Hive has a querying language called HiveQL, right? So HiveQL is much more similar to SQL than Pig. Pig still, you had to learn a few things. Hive is very, very similar to SQL. So what Facebook did was, okay, all of our data is on HDFS. So let people write queries in HiveQL. HiveQL is 95% SQL. I mean, all of it looks like SQL. Then what HiveQL engine does is it takes whatever queries you have written, it converts them into MapReduce code in Java. I think Java, if I'm not wrong. Yes, and it would execute it on the Hadoop distributed system, right? So Pig and Hive made life much more easy because most of the data pre-processing operations, we didn't have to write raw MapReduce code. We could write something in an SQL-like language, and there was an engine which would convert everything that we write into MapReduce jobs. We didn't have to worry about it, which made life simple. Again, Hive just made life very, very simple for many people. Okay, I know people who in the sales team, in the marketing team, who were staring at like petabytes of data, who could run a Hive script and get some data. These are not even software engineers, by the way. Okay, cool. What is a major disadvantage of Hadoop? Major disadvantage. Remember that writing things to disk is very, very expensive. So in computers, right? Your processor is the fastest thing. Your processor is very fast. Then anything that is there in the RAM is very fast to access. Your disk is the slowest thing. And if you look at Hadoop, you're writing to disk many times. After map and shuffle, you're writing it to disk. After a reduce, you're writing it to disk, so on and so forth. Imagine if I have a task where I have to write one map. So suppose it's a sequence of MapReduce jobs. First map function, first reduce function, second map function, second reduce function, third map function, third reduce function. Let's assume this is what I need to complete my whole job. Okay, not just one MapReduce, but a sequence of MapReduces. Now imagine after mapper, there is a diskIO here. After reduce, we will again store in the disk. After map and shuffle, we'll again store on disk. We'll again store on disk. We will store on disk. We will store on disk. See how many times we are reading and writing data from disk. And diskIO takes a lot of time. diskIO is much slower than reading from RAM. And very importantly, the whole Hadoop was designed, when it was designed in the early 2000s, the RAM on most computers was low. People were using 2 GB of RAM. 1 to 2 GB of RAM was what was common in those days. 8 GB, 16 GB, 32 GB of RAM was not very common. Right? That's important. Iterative algorithms, as I told you, as some of you who already have progressed a little bit in machine learning algorithms, most machine learning algorithms are iterative. What I mean by iterative here is, let's look at logistic regression. You have a weight vector that you keep updating. Weight new is weight old minus eta times derivative of s with respect. So this is your formula, right? You keep repeatedly doing the same operation over and over and over and over again. Right? This is, again, if you don't know this, don't worry. You learn it when you learn logistic regression. Right? This is a very simple update rule. You keep doing this in a for loop. So iterative algorithms are very, very cumbersome because each iteration typically is written as one map and one reduce job. So first you run map and reduce, then again you run map reduce, then again you run map and reduce. So each iteration is written as a sequence of one map and one reduce. When you have this, there is one diskIO here, there is one diskIO here, which means the diskIO is just massive if you do iterative algorithms. Again, I have written logistic regression. I have implemented matrix factorization algorithms on Hadoop. Like, not me, as in my team. And I've played a very important role in implementing some of these from scratch, right? Using actually map and reduce functions. And it's a nightmare, folks. It's a nightmare. It takes, it's very easy to implement them. It took us like 1 or 2 days to implement some of this stuff, but it would take forever to run because diskIO was killing us. Again, that's very simple to understand, right? First iteration is map. After map, you write to disk. Then you have reduce. After reduce, you again write to disk. Second iteration, map, you write to disk. Again, reduce, write to disk. Third iteration, so on and so forth. So what was happening is 90% of the time was being lost in reading and writing from disk because this is extremely slow. This was one of the biggest problems. Again, there was this library called Mahout, which was building machine learning algorithms on Hadoop. It was terrible, by the way. It was very, very bad because it would take hours and hours to just execute some simple, to even train a decent logistic regression model would take hours, right? And we wanted things to be fast. That's where Spark came up with a very ingenious idea. Again, by 2013, the world has changed a lot, especially from a computational standpoint. We started having more RAM in the computers. In the commodity boxes that you could go to a store and buy, 8 GB boxes became 16 GB boxes became very, very common at this time, especially in large companies like Amazon, Google, Facebook, etc. Now imagine if I have a 1000 node cluster or a 1000 box cluster, each of them with 8 GB of RAM. The total distributed RAM that I have is roughly 8 terabytes. Wow, that's humongous amount of data, right? We know that RAM is much, much faster than disk. So the simple idea that the designers behind Spark asked was this: why don't we store everything in RAM? Why are we storing things into disk? Right? Very simple concept. And they simply said, whatever is being done with disk, we will also use duplication or replication for resilience or for fault tolerance. And the idea is very, very simple and elegant. The idea is this. Look at this. The idea is very, very simple and elegant. The idea says, imagine if I have some data set D, right, which can be broken up, or a data frame. Let's say I have a pandas data frame, just for simplicity, okay, which can be broken up into 3 pieces, D1, D2, D3. I can store D1 in the main memory or in the RAM of this computer. I can store D2 here. I can store D3 here. Now, just like the way we have done with disk, I can also create duplication or replication on the compute in the memory. So what I'll do here is I will store a backup of D2 in the RAM here so that if this box goes down, I can use this, whatever data is there here, if this box goes down, right? So the same concept of replication or duplication is used for resilience or fault tolerance. Again, any distributed system, you have to think of fault tolerance. That's very, very important. Okay, cool. So next thing is, they created a very interesting concept called as RDDs. Okay, Spark is completely built on this concept of RDD. What is an RDD? RDD means a resilient, which means it avoids fault tolerance. It facilitates fault tolerance. Resilient means if a system goes down, I'm okay with it. It uses distributed data sets. So RDDs are basically immutable. What does immutable mean in Python or any programming language? It means something that can't be changed, right? It's immutable collection of objects. You can take any Python object, any Java object. You can take any object, and that is stored as a distributed data set, which means it is not stored in one computer. The whole object is broken down into smaller pieces. It is stored across multiple boxes in the main memory or RAM, right? And it is resilient, which means it ensures that even if a system goes down, it can make it work. Okay, that's the whole concept. As far as the file system, Spark can use HDFS. Spark can use many other distributed file systems, but Spark works very well with HDFS. So whatever we learned about Hadoop distributed file system, Spark can just use that. And the whole idea behind Spark is, imagine if I have an iterative algorithm, right? Imagine if I have an iterative algorithm. Let's see how that actually works in a Spark environment. Let's get a high level overview, then I'll show you some code also. Don't worry about it. First, I want you to get the concept first. Okay. I'll also do code walkthroughs in the future sessions. Some even here. Okay. First, let's get the concept. That's very, very important. Suppose my whole data is on distributed file system in the disk. This whole thing is first loaded into the memory, right? Everything is loaded into memory. Imagine, okay, so let me just draw it here for you. Imagine I have these three boxes, right? Imagine I have these three boxes which are connected via a network, right? This is compute, memory, disk, compute, memory, disk, compute, memory, disk, right? So whatever data I have here, some part file here, some part file here, some part file here, right? First, I read this, I convert this into a data structure called a resilient distributed data set. I load this whole data into my main memory, right? Into a distributed main memory. Remember, my main memory right now is distributed. Some part of it is available on this computer, some part is available here, some part is available also here. So that's why I'm calling it as a distributed memory. Now, since the data is in the memory, I perform my first iteration here, right? Again, to perform the first iteration, I can still use MapReduce. But the result of the first iteration, I don't store it on disk. I again store it back onto a distributed memory using another RDD, right? So my initial data is, let's say, RDD1, right? I load everything from disk and I create, let's say, RDD1. RDD is nothing but a resilient distributed data set. Data set is basically any data set that you have, any data that you have. Distributed because it is distributed across the main memory of multiple boxes. Resilient because in case some box goes down, it can handle it internally. So now whatever is the output of this, it is stored in the distributed main memory only. It is not written to disk, remember. Then you perform your second iteration. For the second iteration, the data is all in the distributed memory. So you can perform the second iteration. So on and so forth, keep performing your iterations. The last output you store it to your HDFS or the disk. So now if you notice the diskIO, there is only one time you're reading from the disk, one time you're writing from the disk. You're trying to store everything now in the memory. And why are we able to do it? Because of two very important reasons. One, our memory, our distributed memory. Imagine if I have 1000 boxes with 8 GB RAM, I have 8 TB of memory, distributed memory. That's like humongous. You can store massive data sets with this, right? So whole of Spark is designed around this concept of RDDs, which are basically distributed data sets that are stored in the main memory. That's the big leap. That's the major leap. There are some other improvements also. Now, again, this is a very nice diagram that I've taken from a talk at Stanford. Again, please, I'll share the link with you. This is by Rezab, who was one of the creators of Spark's machine learning library. He was a PhD student at Stanford, a phenomenal candidate. Okay, very, very smart guy. So this is a diagram that I've taken from his slides. Okay. So now the quick question that you should ask is, okay, what happens if a box shuts down? Let's ask this question. Okay. What if a box shuts down? Or what if some memory gets corrupted? Suppose you have some data in the RAM gets corrupted. What happens then? Very, very important question, right? Okay. You can fetch the data from some other computer. Okay. Again, Spark also uses the MapReduce concept. Okay, I'll show you how the concept of MapReduce is a very general concept in distributed systems, which is used both by Hadoop and Spark. Spark, in addition to map and reduce, it does other operations also. So what it does is this. Suppose on this box, look at this. On this box, okay, I have some part of the RDD that I'm storing. Okay, so let's assume there is an RDD here. RDD, some part file. Let's say part 2. Some part file of the RDD is stored here. Suppose this memory gets corrupted or this box goes down. Now, the whole Spark engine has to recompute this sometimes. Or if it's available on another box, it will pick it up. Imagine the duplicate or the replication is not available for some reason or multiple boxes failed. what it does is it tracks the lineage info of the RDD. In other words, it says, how was this RDD generated? What all operations went in to creating each of these RDDs? So it knows that, okay, from this file, I read some data, I performed some operation, this data came here. From this file, this is a symbol for disk basically, okay. From this disk, I read some file, I did some operation, and this came from here. This came from here, and it came from here. So if this box goes down, okay, if this box goes down, Spark realizes that I've lost this, but I can recompute it because I have the whole graph, or I have the whole lineage of how this whole part file was created. This is one of the strategies that Spark uses to create fault tolerance. Okay, it uses the whole lineage, which says for every RDD part file, it knows what operations created this. Right? It stores that info so that in case something goes wrong, it will just rerun those operations. Cool. Now, okay, so there is a so iterative algorithms. Again, for now, just remember that Spark can also use same concepts of map and reduce. Now, Spark is also very, very popular for interactive apps. For example, I want to plot some data. Okay, I generate one plot. For example, I'm doing some data analysis. I have some data on the disk. First, I will load this whole data into the distributed memory using an RDD. Now, after this, I want to probably run multiple SQL queries because I'm doing data analysis, right? So I can run one query first. I get the output. Based on this, I want to run one more query. Remember, because the whole data, if it fits into the distributed memory, if it fits, then you're not reading from disk again. You're only reading from disk once. You're only reading the data from disk once. You can perform these iterative operations, or sorry, interactive operations, not iterative, I'm sorry. So suppose you have 1 TB of data. You load everything into your distributed memory. You run one query. You get an answer. Now, based on that answer, you want to run one more SQL query, or you want to generate one plot using this whole data. Because this data is there in the distributed RAM or in the distributed memory as an RDD, these things will run much, much faster than Hadoop. Again, please look at it. Again, this image itself, even though I've not copied it, is inspired from the talk that Rezab gave at Stanford. Okay, cool. So there is another thing, which is if you want to write code in Spark, Spark itself is built in a programming language called Scala. Again, I mean, Scala is a little tricky to learn if you're not very comfortable, but Scala itself runs on Java virtual machine. Okay, don't worry if you don't know what Java virtual machine is, but you can write Spark code in Java, you can write Spark code in Python, you can write Spark code in R, which is a statistical programming language. So you don't have to, in the early days of Spark, everybody had to know Scala. So I wrote some Scala code myself. But slowly they realized that a lot of data science folks don't want to learn Scala. So they created something called as PySpark, which is you can write all your code in Python by just importing a library. Everything will be in Python, but whatever code you write in Python, it will finally get converted to Scala and get executed on Spark. Right? PySpark is slightly slow, but it's much, much easier to use. So I recommend that you use PySpark only, because again, if you know Scala or if you know Java or if you know R, you can also use that. Cool. Now, I told you a while ago that the two most important operations of Hadoop is map and reduce, right? Similarly, and there are only two operations basically. There is something called partition and all, but let's not go into the depths of it. As far as Spark is concerned, they have a slightly larger list. They have the map function, which is exactly like the map, just like exactly like the map in MapReduce. The reduce here is called reduce by key. They have something called filter also. They have a bunch of functions. There is a huge list of basic operations that you can use. Right? I'll show you some examples in a couple of minutes. Okay, I'll also share this whole document. So let's look at a few examples. Okay. Okay, so look at this. So there are a bunch of, again, this is some code that is written here. Don't worry about the code much. Okay, look at this. So imagine if you're RDD. So this is very nice example. I really like this page because it gives a very nice example of what happens. Okay, so let me walk you through this example. Okay, so imagine if our data, if our RDD contains key value pairs like this 1 2 3 4 3 6. This is the key and this is the value. This is the key, this is the value. This is the key, this is the value. Suppose this is our RDD. Now if you run this function called reduce by key, if you use this function reduce by key, what it does is it simply does this. So imagine if you have an RDD and if you run reduce by key, what it does here is very simple. Okay, and let's assume you say the function that I want to use, my reduce function, let's just assume my reduce function is, let's say, plus. Okay, let's assume my reduce function is add, which adds any numbers that is given to it. Then if you notice, what does it do? Reduce by key is exactly the reduce in Hadoop. So wherever you have the same key, all of that goes to the same box. So 1, 2 goes to one box, 3, 4 and 3, 6 go to the same box. Now in this box, it will add up everything corresponding to 1. So it will result in 1, 2. In this box, everything where the key is the same, it will simply add the values. Right? It will simply add the values. So what is the output here? You get 1, 2 and 3, 10. This is the output that you will get. Exactly the same concept, right? Reduce by key is exactly reduce in it's exactly reduce in Hadoop. Similarly, there is something called as group by key. Suppose imagine if you give this input and if you call, suppose this whole thing is in some RDD, you say rdd.group by key. What it does is look at the output that it generates. It says the output that I'll generate here is group everything which has the same key. So it generates 1, 2. Look at this, it generates 1, 2. Remember, for 1, the only value that is there is 2. For 3, the values that are there are 4 and 6. So it will group. So group by key basically means wherever the key is same, it will combine all of the values into a list here. Very, very interesting, right? Similarly, you can write a map function, right? Map basically every value that it has. For example, okay, imagine if you have a map, suppose you have map values, okay? Very simple. So in the map values function, we are saying if the input is x, output x plus 1. Very simple. So what is our input here? If you look at the example, this is just increment operation as your map function. If you have 1, 2, it is generating an output of 1, 3. If you have 3, 4, it is generating 3, 5. If it is 3, 6, it is generating 3, 7. So you have map, group by, reduce. There are many other, there is sort, there is get all the values, get all the keys, subtract, join. Again, this join is exactly like the inner join in SQL that we have covered in the course videos. You have right outer join, left outer join, co-group. There are a bunch of functions that you have, bunch of transforms. These are typically called as transforms or basic operations that you have, right? For example, you can just go to Google and search for this. Let me show you. Okay, yeah. So look at this. If you just go here, okay, these are all the functions. You have map, filter. Okay, then you have flat map. There are a bunch of these. These are very simple. You can see most of these examples here. Again, the reason I gave this page link is because they explain with some very nice examples. There are a ton of these. These are all the functions. In Hadoop, you only have map and reduce. There's something called partition also, which we don't use much unless you're writing some complex script. Here you have many more: group by key, reduce by key, join, co-group, Cartesian product, okay, coalesce, repartition. There are tons of these. Okay, so basically speaking, it gives you more operations to work with. And let's see a very simple code example, right? So let's see some simple code examples. Again, right now I'm just doing a simple code walkthrough. In the next live session, I'll actually execute this on my computer. I will show you how to install Spark in the next session and actually execute it on my computer. Okay. Here I just want to give you an overview first. Let's understand the conceptual part. Then we'll do, again, I'll also do some simple code walkthroughs. Okay, this is a very nice page with Spark examples. Again, you can see the Spark code in Python, Scala or Java. Okay, you can see it in any language of your choice. Let's stick to Python. Okay, I'll just walk you through this code very simply. We'll execute it next week. Okay, first I want to give you an overview. Okay, look at this function. It says, so you will import Scala first. So the SC, basically there should be a line here which says import Scala as SC, right? Once you import that, you say sc.text file and you're giving a HDFS path. Look at this, the path that you're giving here starts with HDFS://, which means this is not your thing that is there in C drive or D drive. This is there in the HDFS system that you have. Again, some path that you give. So whatever is there in the So what you're doing here is you're creating an RDD called text file, which contains all of this data, right? All of this data. Next, let's look at what this line is doing here. Okay, let's look at what the flat map is very similar to map, so don't worry about it. Okay, so what it's doing first is, again, I hope all of you know about the lambda functions in Python, right? If you don't know, let me do a quick cover of, let me just quickly cover. I hope you have done at least I hope you know that. Okay, so just let me tell you what is a lambda function in Python in case you've forgotten it. In Python, you can write like this. You can say x, you can use the keyword lambda. These are the parameters and this is the output. So if you write like this and if you say print x3 comma 4, look at this. If you say, so these are the parameters, this is the output that it generates. This is what gets executed. Think of it like a function. Lambda functions are a concept in Python that we have discussed in our course videos also. Right? So what it does here is, if you call this x, remember x is not a variable here. X is the name of the function. Right? So if you say x3 comma 4, this 3 becomes a, this 4 becomes b, and what it returns is a star b. These are what are called as lambda functions in Python. And lambda functions are what you see in Spark code a lot. Okay, so look at what it says. It says, first, given the text file, look at the steps that it's doing. First, it's running this flat map, which is very similar to map. It says, get each line of the text file and split this. Again, this whole code is for counting the number of words that we saw earlier, right? We saw how to do it using MapReduce. I told you the logic. To count that in Spark is literally, in PySpark to be precise, is literally the 6 lines of code. Maybe a couple of imports and saves. That's it. Save is also there. You just have to import it. So here you are loading the data into an RDD. Now you are saying you want to execute a map function. What does it do? It takes the line. It takes each line that is there in the text file. It splits the line by a space, which means you are getting individual words now. Look at this. It's splitting everything by the blank space. So what do you get now? You get the individual words now. You get individual word 0, word 1, word 2, word. You get the individual words after you split by a space. Right? Now after that, what do you get? Next, I'm running the map function. So here I'm writing one flat map followed by a map. Think of flat map as just a map. That's the simplest way to think about it. Slightly different from a map, but don't worry about it for now. Okay. Next, what am I doing here? I'm saying next, what is my map function? This is my map function. See, look at this. It's so simple to write PySpark code. This is my map function. This is my reduce function. Right? My map function says, okay, after it is split, I'll get each of the words. This, for each word, I will output the word comma 1. So I will output the word. Okay, so let's assume there is word 1, right? I will output word 1 comma 1. If I have word 0, I'll output word 0 comma 1. If I have word 2, I'll output word 2 comma 1. So this becomes your key. This becomes your value. That's how MapReduce works, right? Then look at your reduce part now. What is the reduce part doing? Reduce is saying reduce by key. Okay, again, remember that the same word can occur multiple times in your data. So this map function will generate word 0, 1, word 1, 1, so on and so forth. Reduce by key. When you say reduce by key, wherever the key is the same, they all will go to the same box. Wherever the key is the same, these two will go to the same box, or even this. All these three will go to the same box. This will go to the same box. In reduce by key, shuffling already is happening. The moment you use reduce by key after map, shuffling happens automatically, internally. You don't have to write the shuffle code. Now, what is my reduce function? My reduce function says, given 2 inputs, look at this, given 2 inputs, please add them. That's all it's saying. So what will happen now is, okay, what will happen now is, these ones, look at this, if W0 occurs 10 times, you will encounter W0 comma 1 10 times. So these ones are getting added here. These ones are literally getting added here. So this A and B are basically the values that you have. So it does 2 at a time, and it adds all of these. So you're giving the add function, adding the values as the function for the reduce. Now once you generate this, so this whole sequence, look at this. First you used a flat map, which took a line, which split it into individual words. Then for each word, you created a count of 1. Then you summed up the counts. 3 lines. And the final result is in counts. right? All this is in memory. Look at this. It will not write anything to disk. It will try to keep everything in memory and it will shuffle using the LAN. Oh, one more very important thing that happened in Spark as Spark became more popular was the LANs themselves. The LAN connections became very, very fast. So nowadays 10 Gbps LAN is not unheard of. It is very, very common today at large companies. Right? So LAN became also very fast. So whatever is there in the memory, if I have to shuffle it to another place, I can do it very, very fast today. Right? Finally, whatever is there in my counts, I want to save as a text file in a Hadoop file system. Done. So word count in Spark is literally the 6 lines of code. I'm doing a high level code walkthrough here. What I'll do next week is I'll install Spark on, Spark. I'll install Spark on my box locally in a single box instance, and I'll show you how to make it work. Okay, cool. Again, there is a lot of code here if you want to use. Very, very interesting code, but I want to give you an overview first. Cool. So again, more examples you can read up here. And again, we'll see a lot of examples when I do some code walkthroughs. Okay. Again, I want to prioritize on the most important topics also. Cool. So you have RDD as the basic structure that was designed with Spark, the very earlier versions of Spark. But the creators of Spark quickly realized that Spark is being used a lot by data scientists, machine learning engineers for large scale data analysis. So they created something called as a data frame. On top of RDD. Because the reason they created this, again, I really like the flexibility of the concept of RDD and the designers of Spark. They said people are using pandas data frames anyway. Lot of data scientists use pandas data frames. They also use tables in SQL. So what if we create a data type called data frame, okay, and it has an API of its own, which means I can run a bunch of functions on these data frames. Instead of people worrying about RDDs, let's create one more data structure called data frame, which is built on top of RDDs so that data scientists don't have to know about RDDs. They just use the data frames, very similar to the way they use tables in SQL or very similar to the data frames that they already use in pandas. So today for most data science and machine learning applications, data frame is what is used extensively. And it is better suited for data science applications because what it represents. Again, we have seen in our course that we use pandas data frame extensively because it can be thought of as an SQL table or also as a data matrix. Okay, this is something that we cover in our course videos as you progress through the course. If you're in the early parts, this may not make sense, but you'll get used to. You'll understand what is a data frame in pandas by the time you finish the first, and what is a table in SQL by the time you finish the first module. Okay, cool. So today data frame is a much more widely used data structure than RDD. Okay, we looked at lambda functions. Okay, let's look at a slightly different example. Okay, so imagine I have some data and I want to do a simple search, simple text search on this using Spark. Okay, again, this code has been taken from the examples. I've just taken it and pasted it here. Let me walk you through high level. We'll see the execution of the code later, but I'll walk you through it first. Okay, suppose I have some data in my HDFS. Again, when you install Spark, HDFS also gets installed for you. So don't worry about it. Okay, it gets installed on the system of boxes that you have. Again, very often as a data scientist or a machine learning engineer, you don't have to worry about the installation of Spark. That is typically done by your operations engineers or software development engineers. Often, again, I've been in situations where I installed Spark because we were one of the earliest users of Spark on some of our clusters. But I took a lot of help from our software development engineers and operations engineers in doing so. So very often you don't have to worry about installing Spark itself, but I'll show you, I'll share a quick tutorial next week about it, right? So let's go into this, right? So what does this say? We'll import Spark. Spark, read this text file, right? Next, look at this. In this line, I'm creating a data frame. Let's look at how it works. Okay. So look at the map function here. Look at what is there in the map function. The map function says, look at what it does. The map function simply says, whatever is there in the text file. Okay, whatever is in the text file, each line convert it into one row of data. So each line, suppose imagine my text file has line 1, line 2, line 3, line 4, line 5, etc. Converts this row function, converts this whole thing into one row. Okay, that's what this function does. Again, this row function is available in the data frame structure of Spark itself, right? So first thing that it's doing here is it is converting each line into a row, and it is also running this function of to data frame. So what this does is, so whatever you have here, see, look at this, what you have here is still an RDD. By the time you execute this, what you have here is still an RDD. Now we are converting an RDD to a data frame. When you convert an RDD to a data frame, you should say what are the column names. So initially what did we do? We took whatever is there in the text file. We created each row, each line basically, each line of the text file. We wrote it as row 1, row 2, row 3, row 4, row 5, etc. But I have to give a column name also. So this line becomes the column name. Okay, so basically a data frame should contain rows and column name, right? So here what it's saying, I have an RDD, I'm converting an RDD to a data frame, right? Because when I load it, what I get is an RDD, not a data frame. I'm saying the name of this column is line. Now what I have is a data frame. On data frame, there are a lot of very simple operations that you don't have to worry about. They all these operations get executed in a distributed fashion. You don't have to write map, reduce by key, all that code. Look at this line. It says data frame.filter. So data frame, just like in pandas, again, just very similar to pandas, you can filter the rows, right? And it says take all the data which is there in the column line, and this is like a grep, like, if you recall, like, right? Like is used to grep things. So wherever you see the keyword error, look at this, wherever you see, whichever line, because what is the data frame now? Each line here, and this, the column name is line, and this data frame is called DF now. So it says within the DF, you filter it, you take the column name, in this column name, wherever you have error, filter all of those and create a new data frame called errors, which only contain those lines which contain the word error. Now you can do errors.count. This is very similar to pandas, right? This will tell you how many lines are there which contain an error. Very similar, right? Similarly, if you want to count errors mentioning MySQL, very similar. Look at this. You have errors, errors.filter. Look at the column name line, and like. When you say like, wherever there is this keyword MySQL in the erroneous lines, you get all of them and then you count it, right? So the Spark data frame is very similar to a pandas data frame. The beauty of it is it has a bunch of functions for you. Again, you can see some more examples here. We'll discuss about the Spark data frame in more detail with more examples in the next week or the week after that sessions. Okay, the core idea that I wanted to walk you through is the data frame concept in Spark is very similar to the pandas data frame concept. Of course, the functions are slightly different, but the concepts are very similar. It's as if you have a bunch of as if you have some data set and on which you are running things. Now, okay, those of you who know how logistic regression works, I wanted to explain how you can convert logistic regression into MapReduce framework. Okay, this is a very interesting exercise, I know. Okay, so before we jump into it, let's take maybe 3-4 minutes break. We are already running short on time. Let me see how much notes I have. Logistic regression results. Okay, I think I can finish this. Okay, so let me do one thing. I'll finish this, then we'll do Q&A. Okay, so those of you who already have gone through the logistic regression videos in the course, who knows the mathematics behind logistic regression, let's understand the logic behind how to convert logistic regression into MapReduce. In the coming weeks, in the future sessions, we will actually implement logistic regression using Spark. Okay, we'll do that. But I want to explain the concept first. Okay, so because I want you to appreciate the concept and the power of map and reduce. That's very important. Okay, let me tell you. Okay, so logistic regression basically is you have a weight vector that you want to keep updating. It's an iterative thing. You run this iteratively. In each iteration, you create a new weight vector, which is the old weight vector minus a some learning rate. Okay, this is your learning rate multiplied by the derivative of L or the loss function with respect to W at W old. Now this whole thing, you can write it as a function. Again, if you have gone through the logistic regression videos of the course, you can easily recognize that this itself, if you write the equation for it, this will look like summation of I equals to 1 to n, where n is the number of points that you have in the training data, right? And some function, you'll have a function like g here. Again, I've written it in general terms and I didn't write the actual expression because this type of update function is common for logistic regression, for linear regression, for deep learning algorithms. The same is the concept. That's why I'm trying to explain it in a general terms. So this whole chunk that you have here, which is the partial derivative of L with respect to W, is nothing but computing a function g across all the data points, right? So imagine if I have 3 boxes. Okay, let's see very simple idea of how to implement logistic regression. Imagine I have 3 boxes, box 1, box 2, box 3. What is the simplest way of distributing it? If my n is large, let's assume n is 1 billion, or let's assume n is 3 billion data points, and I have 3 boxes. Okay, what if, again, what is the most computationally expensive part? This is d-dimensional, this is d-dimensional, this is a scalar. The most time consuming part is computing this partial derivative, or in other words, computing this summation. Evaluating this function is also very easy. This is just a simple function. Evaluating and summing up these values. So you'll get g of w, x1, y1, g of w, x2, y2, and so on and so forth. You have to sum up all of them. That summing up is the most cumbersome part because you have 3 billion points across which we have to sum up. That's the most computationally expensive part. So the idea here is, what if I have 1 billion points here, 1 billion points here, 1 billion points here. In each iteration, again, every iteration, in the very first iteration, I load all of this data to my memory. I load all of the data to my memory, right? Into RDDs or data frames. Let's use data frames. That's easier. That makes life easy. Now, in the compute part, what I'll do is I'll compute this function. Look at this. I'll compute this function on the 1 billion points that I have here, on the 1 billion points that I have here, on the 1 billion points that I have here. On these 1 billion points, I'll compute it on this compute, or on these processors, on these processors, on these processors. So in my map stage, what am I doing? Imagine if there are n1 points here, n2 points here, n3 points here. n1 is 1 billion, n2 is 1 billion, n3 is 1 billion. If there are n1, n2, n3 points on the first computer, on the first box, or the first node of the first computer, I'm going to compute across all these n1 points, what is the summation? So what do I have here? I have summation of I equals to 1 to n1 g x comma w i comma, w comma xi comma yi. So on these 1 billion points, I have the sum. On these 1 billion points, I'll compute the sum here. On these 1 billion points, I'll compute the sum. In the reduce stage, what I'll do is I'll get this sum, and this sum. All these 3 sums, I'll get it to a single box, which means I'll give the same key. At the end of the day, if I give the same key, so whatever is this partial sum is the sum of all the values on these n1 boxes. I will put it as value here. I'll give the same key. Let's assume I give a key of 1 here also. I give a key of 1 here also. I give a key of 1 here also. Now, if I say reduce or reduce by key, all of these partial sums, I'm calling it a partial sum because it's a sum of n1 points. It's a sum across n2 points, sum across n3 points. All these will come to a single, these sums, we are not transferring all the data. We are only transferring these sums to one box. Here, I will just sum it up. Once I sum it up, I get this whole big summation. Once I get the summation, performing W new equals to W old minus eta times this, because I already have this will take no time. Right? Very simple. Once I do that, one iteration is done. At the end of the iteration, I'll store all the results. I'll store my W old, W new. I will store all of them on in these memory only. I will not write anything to disk. Right? So this is how you can easily distribute logistic regression itself, or any optimization based machine learning algorithm, not just logistic regression, linear regression. Of course, trees are a little tricky. Trees are not that easy, but any deep learning algorithm also you can easily distribute using the simple mechanism. It's extremely simple. That's why I told you, right? You can implement logistic regression in Spark from scratch using map and reduce in less than 15 lines of code. You can literally implement it in less than 15 lines of code. Okay. So now, okay, so this is again taken from Rezab's slides based on a talk that he gave at Stanford. Look at, okay, so look at this plot. This is very interesting. So they built a very simple logistic regression model. The x-axis here is the number of iterations. The y-axis here is the total running time in seconds. Okay, so they have used 100 GB of data on 50 boxes. So these are m1.x large on EC2, on Amazon cloud computing boxes. So they've taken 50 boxes, they've leased 50 boxes on AWS or Amazon Web Services, and they had 100 GB of data. Look at this, when they had one iteration, again, this is the time for Hadoop, this is the time for Spark, right? So Hadoop roughly took 110 seconds per iteration. Spark, first iteration took 80 seconds. Why did it take 80 seconds? Think about it. Because in the first iteration, both Hadoop and Spark have to read from disk. In the first iteration, whether it is Hadoop or Spark, they both have to read from disk, right? So there is not significant difference. But as every further iteration took only 1 second here. Here, every further iteration would take 110 seconds because it has to write the data to disk, read it again, all of that stuff. So if you have 30 seconds, look at this, if you have 30 seconds, if you have to run a model for 30 iterations, this takes 3,500 seconds, while this only takes what, 80 plus 30, 110 seconds. This takes Spark takes 110 seconds, where Hadoop takes 3,500 seconds. Because Hadoop is not writing, so Spark is not writing anything to disk. It's keeping everything in memory. Right? So it's doing phenomenally well. And again, I have seen this impact myself when all of our models, including basic, we had some models, we had some simple logistic regression models, we had some complex decision tree, random forest type of models. When we moved from Hadoop to Spark, wow, the speed up was enormous. And we ended up saving a few hundreds of thousands of dollars in hardware costs, literally. That's how impactful this was for our team. Cool. Now, there is also this very nice slide from the same talk at Stanford, where it says, what if you have lesser amount of memory? What if you have less amount of, how much time does it take for each iteration? Imagine if you have the whole 100% of the RAM that you can use for Spark. If you can use the whole 100% of the RAM for Spark, each iteration was taking, let's say, 11.5 seconds. But if you can only use 50% of the RAM on the box, it was taking 40, because remember, Spark also, it tries to store, the model is this, compute, memory and disk. Imagine if I don't have enough space in my memory to store my intermediate results, I will have to store it on disk. I will have to do it. I don't have an option, right? Within disk, if you are a computer science student, you might know, the disk has two parts. There is something called as a swap space and a file system, right? Swap space, again, Spark, whatever data is not there, whatever data doesn't fit into the memory, it tries to use the swap space, which is slightly faster than the actual file system itself. But if that doesn't work, Spark's worst case behavior is, let's store in file system. So if you say don't use any RAM, you can change it in Spark settings, by the way. You can say, I don't want you to use any RAM to store RDDs. Then it would completely store everything to disk, and it takes roughly about 69 seconds to store the data to disk, which is very similar to Hadoop, right? Look at this. Hadoop was taking roughly 110 seconds per iteration. Probably this is slightly less than that because it is using the swap space and not storing everything into HDFS. Okay, that's the understanding. Cool. Now, okay, so let me give you the big picture view of things. Okay. Spark itself, whatever transforms that you learned, map, reduce, all of that falls in the Spark core, right? Again, as a data scientist, you will not write Spark core code much. You will not much, right? Because there are a lot of other tools in Spark that will make your life easier. Okay, you don't have to write code using map and reduce every time. Okay, that's one of the best parts of Spark because they've implemented most of the functionality that we need on day-to-day basis. There is something called Spark SQL, which is basically you can run SQL commands on data that is there in data frames. So whatever you have in HDFS, you load it to an RDD, which you convert into a data frame. Now, whatever is there in a data frame, you can think of it like a table in SQL, and you can run SQL queries on it using Spark SQL. This is very, very useful. This is very, very useful because all of the data pre-processing, all of that, you can do it using Spark SQL. And in practice also, people use this. Nobody writes Spark core code using MapReduce anymore. Data frames, SQL, everybody knows SQL. It's much, much easier to use. Of course, whatever SQL you are writing internally gets converted into Spark core code and gets executed. But why do we have to worry about it? Similarly, most machine learning algorithms, when Spark was very young product, right? We implemented a lot, at least our team at Amazon, we implemented a lot of these machine learning algorithms using Spark core. We wrote Spark code in Scala actually in those days. Now you don't have to do it because people like Reza, whose slides I have borrowed in a couple of instances, have written MLlib. You have most of the major machine learning algorithms from logistic regression, from matrix factorization, recommender systems, ton of algorithms are already implemented. It's just 2 lines of code. You don't have to, again, in reality, in most situations, you don't have to implement the logistic regression from scratch in Spark. In most real world situations, but it's good to implement it once to know how it works. Then there is Spark streaming, which is mostly used by analytics teams, which means imagine I'm getting a huge, take Twitter as an example. That's a good example. People start tweeting. So there is basically a stream of tweets. And based on the stream of tweets, you want to build some analytics. You want to say, hey, what is the, let's say very simply, what is the, what is the trending hashes, right? Trending hashtags on Twitter. People put hashtags on Twitter, right? So what do they have to do? All the data that is coming into Twitter, they have to run quick analytics on top of it, which is basic. What does analytics mean? Simple group buys, simple counts, and etc. So for that, Spark streaming is used. Again, Spark streaming is not used as much by machine learning and data science teams. They're mostly used by analytics teams. We'll touch upon Spark streaming also briefly. Then Spark also has something called as GraphX, which is mostly used for graph processing. For example, you want to run the PageRank algorithm. Again, we have a case study in our course videos which uses graph processing algorithms or graph-based algorithms, wherein we say, okay, wherein we take some data from Facebook and we say, can you recommend who should follow whom, right? I think it's Instagram data, not Facebook data, but same. Instagram and Facebook are owned by Facebook, right? So if you want to do some graph algorithms, there is GraphX. So we will focus a lot on Spark SQL, MLlib, a little bit on Spark core, a little bit on streaming, because in practice you will be using these 2 more. Okay, but knowing a little bit of Spark core also helps. Okay, so in the next live session, as I just mentioned, we'll focus on Spark SQL, MLlib, a little bit of core, if time permits, a little bit of streaming also. In the next session, we'll do more code walkthroughs. I'll also briefly give you a quick tutorial on how to install Spark on your box. Again, it will depend on whether you're using Linux, Windows, all of that, but I'll try to come up with a simple mechanism to do it. In the meantime, if you want to read some very simple programming guides about Spark SQL or Spark MLlib, here are some good resources. Again, let me show you how easy it is to write Spark MLlib code. For example, you want to train, let's say, okay, all this is math, don't worry about it. If you go to the code, this should be straightforward, right? Okay, see, if you want to train logistic regression model, let's see how simple the code is in Python. It's really, really simple. Okay, let's look at this. You're importing a bunch of things. From PySpark, you're importing logistic regression with SGD. Okay, from PySpark, you're importing something called as labeled point, and from NumPy, you're importing array. Okay, so you're writing this function called parse point. Again, I'll walk you through this in more detail here. I just want to show you how simple it is. Okay, so first and foremost, you're loading the data from a text file, right? Then you're running this whole thing using, again, remember when you load it. Okay, so let me write it here. When you load the data, it's in an RDD. So you're running this map function because whatever data is there in the text file, you want to convert it into xi, yi pairs. Okay, this whole thing is just data pre-processing code. So all the data that is there in a distributed fashion, it will run this map, wherein all of the data that you have, it will convert into xi, yi pairs. and it creates something called as parsed data. And the data type that you need to have is labeled point. Again, I'll touch upon this in the next session in more detail. I just wanted to show you how simple it is, right? Next, if you want to build a logistic regression model, it's this simple. Logistic regression with sgd.train. What data do you want to train? Parsed data you want to train it in. You get your model. That's it. You got your model. Literally one line of code. This whole thing is loading the data. This whole thing is pre-processing the data. Modeling is one line. Now, if you want to get the outputs, you can again, just a couple of lines, you'll get the answer. Okay. Again, we'll walk through this in much more detail in the next session, but I just wanted to show you how simple it is to write Spark code. If you know basic programming, and if you know, again, the functions change, the concept doesn't change much, right? So if you have time, please go through this. Let's quickly take, again, I'll take a quick water break and I'll try to answer as many questions as I can. Okay, cool. Okay, there are 60 new messages. Okay, let me see how many I can answer today. Okay, where are we? Okay. I have a question. What happens if machine goes down while replicating the data? Again, when you load the data, that's a good question actually. When you load the data, if things fail, it will simply say, it will give an error and you'll have to load the data again. When replicating happens, if things break, it will try to replicate again. Again, depends on what type of replication we're talking about, right? For example, when it is trying to replicate, let's say on disk, okay, suppose this is the disk of one box, disk of second box, disk of third box, and there is a part file here that we are trying to replicate. If during the replication process this thing fails, it will get replicated elsewhere from the original file. So that also happens sometimes, rarely, but sometimes does happen. Okay. What happens if the node crashes while performing the reduce function? The whole MapReduce will restart. Okay. In Hadoop, even in Spark, the same thing happens. Okay. Can we write MapReduce code in Python? Yes. You can write it in any language of your choice. So, okay. So you can write it in any language of your choice. Okay. If you want, I can just show you. I mean, you can easily find some quick tutorials if you want Hadoop Python MapReduce. I'm sure. Okay. So yeah, here comes the code. You just have to implement. Okay. So there is, okay, word count.py. If you look at the code, okay. So this is your mapper. Look at this. This is the code that he has written for mapper. I mean, if you remove all of these, comments, it's literally 4 lines. Okay, this is the mapper.py that he has written. Reducer.py. Again, mostly handling boundary cases and all that. So you can write your mapper and reducer, and when you want to execute it, you can trivially do it. Okay, so don't worry about writing code in Python. I told you I wrote code in Perl, I wrote code in shell script. You can write in any programming language. Okay, is big SQL different from Hive and Pig? Yeah, so Hive and Pig are more generally used in the industry because they're open source, they're very easy to use with. Okay, what if you use SSD instead of RAM, more memory and more speed? Yes, but SSD is, as rightly pointed by Hitesh, SSD is much more costly than disk. But again, the recent versions of Spark also are optimized for SSD, but RAM is way faster than SSD, as Ankit mentioned. Good job, guys. Let me just zoom in a little. Okay. Okay. Can you shed some more light on RDDs? What's the format? Is the result of the box RDD? Again, I don't want to go into the distributed system internals of RDD because we are not a distributed systems course. For all practical reasons, you can just think of RDD as a distributed data store, which is distributed across the RAM of all the computers with some resilience built in. I mean, I think that's the simplest way to understand it. We can keep going deeper and deeper. I mean, there were instances where I went and read the source code of how RDD is implemented, but I don't think you need to do it unless you have ample time of it. Okay. So again, this is not a distributed systems course, and hence I'm trying to give you a high level overview here. Okay. Can't we use HQL for it? How different? Yeah, good question. So a lot of people, very good question actually, Chandan. So on Spark also, if you have Spark, which is built on HDFS, you can use Hive with Spark, just like the way you can use Hive with Hadoop. So a lot of people nowadays, what they're doing here is, on the same distributed framework, they have HDFS, they have both Spark and Hadoop installed. They use Spark wherever they want speed. And by the way, just like Spark SQL, you can also use Hive. Again, Hive has also gotten updated over the years, so that you can use Hive on HDFS with Spark model instead of Hadoop. You can do that nowadays. Okay. Don't we have any way to specify delimiter? Again, every line, the end of line is used as a default delimiter. Again, we'll walk through more code. You'll understand that better. What will happen if you do weight update in each box itself and average the weight? That's another way of doing distributed training. Yes, this is another model that is also used. Very interesting model. Good. I mean, Ritesh, that's a good point that you raised, which is we have each of these boxes. So let's assume I have 1 billion points here. I have 1 billion points here. I have 1 billion points here. I build my whole model just on the single box. I don't do any transfer. So let's assume I get weight 1 matrix. I get weight 2. Same. I train my logistic regression model on this 1 billion points. I get W1, W2 and W3. So Ritesh is saying, why can't I just average this? Okay, just take summation of W1, W2, sorry, okay. W1 plus W2 plus W3, basically take the mean of them. That is one way you can compute, and it's also a very popular way. This is one way of doing it. The other way is what I mentioned. This is surely one way of doing it. No doubts about it. Okay. Can we access the live session later? Yes, you will be able to access it. We'll add it to our course videos by tomorrow. Won't Spark SQL be slower than writing the same on Spark Core? I think, again, remember that implementing, again, Spark SQL itself is implemented. Of course, Spark SQL internally gets converted into Spark Core. And the people who wrote this conversion are the people who created Spark. So their code is going to be way more optimal than you and I writing Spark Core programs. Unless you're an expert in Spark, it is better to use Spark SQL because it's very, very well optimized to convert Spark SQL code to Spark Core code, which works very, very efficiently. They've written phenomenally. Again, I've read some of the algorithmic implementations of Spark SQL. They've done a phenomenal job at it. Unless you are a brilliant software engineer who knows Spark inside out, your core code will not be as fast as Spark SQL, most often. Okay. Can you give a real-time example where Spark is used extensively in the industry? Okay, I'll give the example from my own team. We were building machine learning models for Amazon ads that you see on Amazon website, outside of Amazon website, etc. We were generating petabytes of data. So our models were to be trained on petabytes of data, not even terabytes, petabytes of data. So the biggest challenge for us was pre-processing this whole data. Because this is all logs, text data, log data. We had to pre-process this whole thing, which we often did in Hive or Spark SQL, right? So we would do it in Hive or Spark SQL. After we pre-process the whole data, the final data for the machine learning modeling itself used to be about 50 terabytes. Then on top of this, we had to train models, right? So we had a fairly large infrastructure for Spark, right? So on this 50 TB, we would train random forest, GBDTs, in some instances, a few simple deep learning models also. So we would train all of that. And because we were sitting a lot, again, we were spending a large amount of data in data pre-processing itself. Modeling was actually the easier part. Data pre-processing using, again, we would use mostly Spark SQL and Hive for it, most of the times. Okay, so this is one example, especially in internet companies where you have large amounts of data that are being generated. That's one example that you can look at. Yes. Do you have control over node management? Yes. You can set up everything in Spark. You can say how much disk space you want to use, how much RAM you want to use. You have all that control. But again, that is all Spark administration. That's why I didn't want to go into the details of it. Okay. Along with Spark SQL, what are your thoughts on Spark data frame? Again, by the way, Spark SQL is built to perform operations on Spark data frame. Right, so Spark data frame is the state of the art, works very well. Is the data always in, okay, somebody asked this question, right? Yes, there is also data set that is happening. Again, data set, data frame, all these are being used nowadays, right? Yeah, you can also, there is also something called as data set, which is built on top of data frames, which is also used. Okay, is the data always in TXT file? No, it can read data even in binary form. Right, doesn't matter if the data is in any form, it can read as long as you have the tool that it has to do it, right? Okay, in the current environment, what are the alternatives to Hadoop? Spark. The most popular alternative to Hadoop is Spark. Okay, what is this? Okay. Hey, thank you, Matthias. Thank you for your appreciation. I have 50 systems and splitting data into 50 chunks. Then in each box we have 50 chunks for fault tolerance. Am I right? Yes. Again, the fault tolerance itself, the duplication or the replication factor. So when you're setting up a Spark cluster in the administration, you can say the replication factor. A replication factor of 3 is very commonly used, which means anything that I have in my HDFS, like for example, if this is my disk, if this is there in my HDFS, the same thing will be replicated in 2 other boxes. Sorry, replication factor of 3. Yes, it will be replicated in 3 boxes, not 2 boxes. So replication factor of 2 or 3 is what is extensively used in the industry, right? So if you have 50 chunks, then in total you'll be storing with replication factor of 3, you'll be storing it in 200 chunks. 200 chunks will be stored. Oh, very good. So Google's BigQuery. Again, remember that when Google, very good question, Deepak. So Hive and Pig are open source tools, but remember that Google came up with the whole Hadoop ecosystem. So Google Cloud, Google Compute Platform has something called as BigQuery, which runs on Google's compute platform only. It is built by Google for Google's compute platform only. Not you can't run BigQuery elsewhere. But it is very similar to the concept of Hive and Pig. Very similar, right? Yes, BigQuery also has some ML capabilities that they've added into it. Yes. Okay. In the first iteration, Hadoop and Spark use disk and read, but okay. 1 second. Hadoop continues to write on disk and Spark does it in RAM. What about the time consumption of Spark when it writes to disk? Again, as far as the first read and the last write, look at this. For the first iteration, both Hadoop and Spark have to read from the disk. I've shown that diagram, right? They have to do it. For the last iteration, they both have to write to disk. In between is where you have a lot of advantage, right? You are in PCA. What are the prerequisites to understand the next sessions? Again, I will keep them fairly generic so that, again, because you're already in the PCA section, you'll be able to understand the data analysis, Spark SQL, all of that. Some of the modeling also you can understand because you must have seen a little bit of code from, what do we call it? Code from 1 second, I'm getting slower now. From scikit-learn, right? So Spark ML, so Spark ML-lib. So Spark ML-lib code is very easy to follow if you know the fundamentals that I've just told you enough, and if you know scikit-learn, right? Because the functions, again, at the end of the day, you're writing Python code. The library changes. Don't get stuck to a library. Libraries come and go. If you know the foundations of programming, every 2 to 3 years, new libraries come, you learn new languages, right? How Spark works on image data? Same like text data. You load an image, you do all image pre-processing, you can run all image operations, all of that you can run it, right? Spark also can be made to work on image data. So before installing Spark, do we need to install HDFS? Again, you can install both Spark and HDFS together. Again, Spark can also work on other distributed file systems, but HDFS is the most popular. What if the processes which need to communicate with each other, how does Hadoop handle it? In Hadoop, all process communication happens through map and reduce and shuffle. That's the only thing that we have control of. Okay. What if there is some serial process which needs data from 3 boxes? Again, you write a reduce job which brings all of the data from the 3 boxes to 1 box and computes it. Right. So you in both Hadoop and Spark, you should break down any logic that you have into MapReduce in Hadoop, MapReduce and other things in other core functionality like filter, like reduce by key, those operations in Spark. You have to only use them. Okay, can we use Spark ML-lib on Collab? I don't think so. Okay, do you know any application of Spark for audio data? Yes. So for example, lot of audio pre-processing at some of the top audio companies, pre-processing of audio is actually done in Spark. For example, take any of these, take your Spotify's of the world, right? I'm sure Spotify would use Spark-like framework to do some audio pre-processing for sure. Okay. Do the whole data is stored once in the RAM while the file is getting stored for computation and not in disk, or data is gradually added to RAM for computation from the disk? Again, the data is moved from disk to RAM using the operating system. However, again, I mean, I don't want to go into operating system internals, but imagine if you have disk here. Okay, this is your disk, this is your memory, and this is your compute, right? The whole disk itself is broken down into blocks, right? The whole disk itself is broken down into blocks, and these blocks are placed in the main memory. You don't read everything into the RAM. Whatever block is needed, you read them into the main memory. This is how all operating systems work. Again, this whole thing is built on the standard operating system procedures. So if you know, again, the data moving from disk to memory, Spark internally uses the Linux or the operating system functions to do that. So everything is going to get moved in chunks of data. Okay. Yes, why Hive and Spark SQL are used together on Hadoop? No, they're not used together on Hadoop. Spark SQL is used on Spark, Hive is used on Hadoop, right? So that's a difference there. Hive can be used both on Spark. Hive can be used on Spark and Hadoop. Spark SQL only on Spark. Is it possible to use the benefits of distributed system while using sklearn MLlib? Again, sklearn itself is not designed with distributed systems in mind. So it's not very well optimized to work on Spark. But we have this library called XGBoost that we've talked about in the course videos, right? XGBoost, there is a version of XGBoost that can run on Spark. Very, very fast, actually. Okay. From an interview perspective, good question, actually. What is the breadth we should cover for Spark Hive? Again, the whole purpose we are doing this is for you to have some idea. In an interview, if somebody says, hey, do you know Spark? You can at least give a high-level overview, and just the basic foundational concepts is good enough. There is no point going too deep into it unless you want to learn Spark development. Is it possible for us to use PySpark in your case studies? Again, PySpark, the problem with using PySpark for you would be you need to have a cluster of boxes to actually see the value in it. And getting a cluster of boxes is very expensive. So we don't recommend that. This is mostly to give you some knowledge of how Spark itself works. And in case when you join a company or in an interview, if somebody says, do you know this? Yes, I know the foundational concepts. I'm not an expert in Spark, but I know how the whole ecosystem works. What web material or book is referred to learn about this in detail? Pick any book about Spark. There are tons of good books about Spark from O'Reilly. There is this very popular book called Spark Book O'Reilly. I really like that book. This is the book, Learning Spark. It's a slightly old book, but a very good book. But if you want something better than a book, I would actually recommend going to Spark tutorials. So if you just go to the Spark web page, right? Just go to Apache Spark. Okay, there are tons of programming guides. There is a quick start. There is something about RDDs, SQL, data frames. There is also data sets, structures. There is all this here. So they have a lot of good documentation that you can use. Okay. If the data is stored in distributed system, how do we train deep learning models? Are there any specific libraries available? Again, when it comes to deep learning, it can become a little tricky, but you can run deep learning itself on Spark. So there are some architectures where if you have multiple computers with GPUs, right? So you can distribute the work using Spark across these computers, and within each computer you can have multiple GPUs here. So there is a distribution of work within each box, and there is also distribution of work across boxes. So Spark can also be used in collaboration with TensorFlow or PyTorch or any of them, but not very popular because, again, you want to move the data very, very fast. Even Spark is, it is used in some cases, by the way. I'm not saying it's not used, but the alternative that many people use is just get one box and let's use, let's say, 10 GPUs if you want, okay, or 20 GPUs. But also there are instances where you can't connect too many GPUs to the box, so you use Spark on top of it. Okay. Okay, you've just registered for the course. Don't worry about it. You may not make a lot of sense now. but we'll add this video in the course videos where it is appropriate, and you can simply rewatch this when the time comes. So don't worry about it. What are the advantages of Hive? The biggest advantage of Hive is simple. You write simple SQL queries. So anybody who knows SQL can query Hive. As I told you, we had marketing and sales people in my organization at Amazon, who all learned SQL. And if they wanted to run some SQL query and get some data or do some simple analysis, right? They would just, Hive was so simple because they could just write a simple SQL query and get results. That's the best part of it. How can Spark work on 0% RAM? Again, Spark always uses the swap space on the disk and the disk's file system itself, in the worst case whenever it doesn't have any RAM available. If RAM is not available, it uses the swap space and the actual file system itself, right? So, okay, CPU is not connected to RAM. Yeah. See, Spark will use some RAM. Of course, if you don't have any RAM, it will not work. Spark will use RAM, but imagine if you give it very little RAM, that it can't store the RDDs in the RAM. Imagine if it can't store the RDD in the RAM, it will store the RDD in the swap space or the file system. It will always have some RAM. If it doesn't have RAM, the mapper can't run to start with, right? About parallel programming, yeah, in GPU programming, VRAM is way faster than RAM. Yes, with GPU programming, Spark doesn't work very well because Spark is not designed with GPU parallel programming in mind. So for most deep learning, we use TensorFlow, Keras type of stuff, but there are some, I've seen people using Spark also on top of it, but it's not, again, you have to write code very, very carefully. Okay. How these distributed processing is different from federated learning. Again, the term federated learning itself has multiple definitions, but one definition of federated learning can be thought of as distributed processing because you are splitting the jobs across multiple computers, and distributed processing is a much more commonly used term than federated learning, right? So you can think of both to be similar, but again, depends on what is your definition of federated learning. Okay. Yes, Databricks does have special clusters for deep learning because I've read papers and white papers from Databricks, which is the company that was started by the creators of Spark, where they do that. Yes, I know that they do it, but again, it comes with its own challenges. It's not that straightforward because you have two things. You have VRAM on GPUs, right? You have your regular RAM on GPU. You have your regular RAM. Spark mostly works with this, but Spark also, the most recent versions of Spark also can do some distributed VRAM work. But it is something that is used sometimes, not very often. But yes, I understand that people at Databricks, they've been pitching this for a long time, not enough. I know that they were pitching a deep learning cluster built on Spark, I think 2017, 18-ish. Like I remember hearing from them about it, right? How Spark handles if you have dependency of one iteration and next iteration like gradient boosting? Yes, very good question. So that's also simple, right? In gradient boosting, what do? Gradient boosting is an iterative algorithm. So you have iteration 1, then you have iteration 2. Your iteration 1 will be written as a MapReduce job. Your iteration 2 is a MapReduce job. Iteration 3 is a MapReduce job. All of that, right? Your gradient boosting, the biggest problem with gradient boosting is it's an iterative algorithm, unlike a random forest, right? So your GBDT, think of GBDT as an example of gradient boosting. But I just showed you how to do iterative algorithms like logistic regression. It's the same thing. The beauty of it is at the end of each iteration, everything is stored to RAM or main memory and things will work well, right? Can you show the site on O'Reilly's site? I'll provide you the link. Don't worry about it. I always provide links. So I think this is the example, right? I've already shared this document, by the way. Those of you, you can just scroll up and you'll see this document that I've already shared at the very beginning. Look at this. Yes, I've already shared the notes for today's session. This has all the links, all the references, all the citations. Okay. Do retailers use recommender systems using Spark? Yes, they do use Spark for training the recommender systems models, and I have personally used it myself. So Spark has very, very good recommender systems using matrix factorization approaches built in. So they use it for training for sure. If you have low amounts of data, does it make sense to use Spark? Not at all. If you have small amounts of data, don't use it. Don't waste your time on it. Okay, cool. What is the question here? Yeah, Spark and Hadoop only come into picture when you have at least 1 terabyte of data. Otherwise, it's not worth it. Okay, cool. In continuation to the gradient boosting question, in GBDT, iteration 1 result should be fed into iteration 2. You can do that, right? Look at this. Even in logistic regression, the W new equals to W old minus eta times derivative of this, right? So the output of each iteration has to go into the next iteration. So the next time, see, you do a MapReduce, right? Whatever you have, you store it to your RAM, right? For example, at the end of this iteration, I have a W new, right? But the W new now should be, okay, I don't need it. Okay, fine. In this case, I don't need it. In gradient boosting, if you need it, it's very simple. Okay, so let me explain this. Sorry. In the case of logistic regression, you don't need it. I'm sorry. So in iteration 1, let's assume you got some output. So there is this function in Spark. It's called distribute. No, it's called, I forgot the function name, wherein you can take one output and you can give it to each of the boxes. It's called distribute, I think. I'll have to just Google search for it. So if you have some output and if you want to copy it to all the boxes, you can do that in Spark. So whatever is the output, just copy it to all the boxes. Then you start your next iteration, right? So after map and reduce, or at least a sequence of operations, you just have to copy the output to all the boxes. Okay, I think, again, it's just a Google search away if you just do it. I'll have to look it up. I don't remember it by heart. Spark distribute value across all nodes. Okay, a value optimize Spark with distribute by, yeah, there is also distribute by, cluster by, right? So I mean, it's not very hard. If you just Google search for it and read the documentation, it should be quick. Okay. Okay, there are also some more questions. We'll spend maybe a couple of minutes and then I'll wrap it up. Again, this is I think we'll do a series of 3 sessions on this, and hopefully by the end of these 3 sessions, you will get a decent idea of how Spark works. The first session, I wanted you to get a historical perspective. That's very important on what is Spark, how is it different, what is map, what is reduce, what is shuffle. I wanted you to get that basic idea. Okay, cool. Okay. Is new data getting continuously added to the box as these processes happen? You can do, yes. New data, again, you can store any RDD to these boxes, right? You can always do that. XGBoost, again, if you want to parallelize XGBoost, you are right, Bhargav, that the construction of each tree is parallelized in XGBoost. That's how it's implemented. Okay. How can AI ML be used in security? Probably we'll do that in a general session. But in most security applications or internet security applications, they're using anomaly detection techniques. Right? So there is this whole area called anomaly detection where anything that is not typically observed is flagged for manual review. That's how it's mostly used. Again, it's used a lot in internet security. Can we have one session on end-to-end architecture of retail? What do you mean by retail? I think we have sessions on how, again, in our course case studies, we explain how to build recommender systems. We teach you how ads are placed in a company like Amazon, all of those things, right? Will we do some hands-on in these 3 sessions? That's what I just mentioned, right? In the next session, I'll actually code up a few things and show you the code. Okay. I'll show you how to install Spark. Again, I'll not be able to go into too much depth there because most likely you will not be installing. You'll take help from software engineers or operations engineers in doing it, but we can do it on our box. Okay. Again, you can install Spark on a single box just for your learning, but again, you can install it on a single box and make everything work. So that's one thing. Can we have a session on MLOps? Again, MLOps is very small topic. If you don't know DevOps, understanding MLOps will be hard, but we'll try and think about it. Okay. Again, we are not doing a session on reinforcement learning because there are very few jobs in it, and we want to focus on areas which will help our students get job. Dask or Spark? Very good question. Dask is also very good, to be honest with you. Dask, the beauty of Dask is it can do parallel processing in a multi-core environment. So what the thing that I like about Dask is also a good, it's an up and coming thing. Dask tries to build on top of Spark in some ways conceptually, if not programmatically. Dask can do multi-core, which means imagine if you have an 8-core processor, right? Imagine if you have an 8-core processor, you can install Dask on it. You can do multi-core processing on Dask, right? You can also use Dask on distributed computing. But I think as of today, Spark is a much more mature product than Dask. Okay. Yes, Databricks does give some 15-day trial. Please use it. I'll also try to show using Databricks, but then we'll see how that goes. I want to show you on my box, right? I'll try to explain it on my box. Again, the installation might differ because I'll mostly show it to you on a Mac. The installation on a Windows might be slightly different. Okay, but again, you can always use the Databricks 15-day trial to go through and experiment with Spark. Okay, folks, thank you very much. I hope I've answered as many questions as I can. And see you next week at the same time, and let's continue on the discussion that we are having now. Okay, cool. Thank you very much, and bye-bye.